So geometric sequences series, very similar to yesterday with arithmetic. They're all going to follow the same kind of pattern. And the pattern that we're going to see here is that we have common ratio between our consecutive terms. So it says the ratio between consecutive terms is constant. I have below that written out in subscript notation. That would mean if you were to take the second term divided by the first term, that's the same as the third term divided by the second term, same as the fourth term divided by the third term. So whichever two consecutive terms I divide, I'm always going to come up with the same value. We're going to call that R. So R is our common ratio. Now, I could simplify this in subscript notation and say it's just some a sub n divided by some a sub n minus 1. That's a term divided by the term before it. And then I apologize on recursive formulas. I have made a note to myself last year that the book uses k and k plus 1, not n and n minus 1, like we do in Algebra 2. So we could also write that as some a sub k plus 1 divided by like an a sub k. So that's just saying like a term divided by the term before it. Those things mean the same thing. K and k plus 1 are consecutive terms, or n and n minus 1. So if you are having any trouble with those subscript notations, let me know. Just as another side note, in terms of making connections to things that we have done before, the arithmetic sequences were most like linear functions. And so we saw dn plus c is a lot like mx plus b. Geometric sequence is a lot like exponential functions. So that was chapter 3 when we did exponents and logs. And so that's something like a times b to the x. So our common ratio is really that value of b. The big difference between exponential functions and then sequences is we'll allow the ratio to be 1 or negative 1. Obviously, that's not a very exciting sequence because you're going to get the same term or alternating signs of the same term, but that's okay. And we'll also allow the ratio to be negative, which was not true in exponential functions. The ratio had to be positive, or the base had to be positive. So there is some connection there, but there are some changes. The formula for geometric sequence, or the explicit rule. So if you've been noticing in your homework, if they talk about explicit rules, those are just the rules where you would just have to plug in n and you would get whatever term you were looking for. Thank you. And this is the same formula from last year. So a sub n equals a sub 1 times r to the n minus 1. This is a little bit different than that formula from exponential functions, where we would see like a times b to the x. It didn't have a minus 1 in the exponent. That's because in exponential functions, your initial value was at time 0. In sequences, your first term is at n equals 1. So we're kind of moving that up, and so we need that n minus 1. Think about if you were to put 1 into this exponent, 1 minus 1 would be 0, r to the 0 would be 1, and that would give you your first term. Okay. So there's a little bit of difference there. This should be a quick and easy example for us. We're being asked to do two things. Write the expression for the nth term, for the a sub n, or the nth term of the sequence, and then find the indicated term. So you're doing two different things. Writing an explicit rule, so write the rule, and then plug in n equals a. So this is nice. They give me everything I need, right? First term, ratio. A sub n equals 1 times r, square root 3, raised to the n minus 1. There's my rule, or my formula. You could write this as just the square root of 3 raised to the n minus 1. Right? If your first term is 1, you don't necessarily have to write it out there. So don't be alarmed in your homework assignment if you get some rules and you don't see a first term, and your first term is the 1. Okay, and then to find the 8th term, plug in 8 for n. So 1 times square root of 3 raised to the 8 minus 1. That's really just the square root of 3 raised to the 7th. Of course, if you put this in your calculator, a square root of 3 multiplied by itself an odd number of times is going to be irrational, right? So it's going to give you a decimal. So you could get an exact answer if you thought about it like the square root of 3 times itself 6 times. That would be 3 pairs of square roots of 3. So that would give me 3 times 3 times 3. A square root of 3 times the square root of 3 is 3. And then a square root of 3 times the square root of 3 is 3. And a square root of 3 times the square root of 3 is 3. And I've used up 6 of the 7, right? And then there's 1 square root of 3 remaining. So you could write an exact value for the 8th term as 27 square root of 3. I'm shortcutting this. Right? This is 3. This is 3. This is 3. So you should be able to get exact values if you have a radical square ratio. Now, looking ahead to the next example, what is less nice about my next example? It what? There's no a sub 1, so they don't give me the first term. And there's no r, they don't give me the ratio. And those are the only two things I need to be able to plug into the formula for a geometric sequence, right? Okay. Here is the easiest, quickest way to find r, in my opinion. There are lots of ways to find r, and you can find a way that works for you, that you like. But this is the way I like to do it. Okay, to find r. Take the first term that they give you, which may or may not be the actual first term of the sequence. So the first term they give me is the second term, right? And the second term is 3. Okay. Think in your head for a moment here, recursively. If you had the second term. If you had the second term, and you wanted to get the third term, you would have to multiply the second term by r, right? Whatever that may be, the ratio. And then you would have the third term. Well, we don't know the third term, we know the fifth term, so I would still have to multiply by r again, and that will get me to the fourth term. And then I will multiply by r one more time, and that will get me to the fifth term. So 3 times r times r times r, whatever that may be, is 3 over 64. If you were going from the fourth term to the 10th term, you'd be taking r times itself 6 times, r to the 6th, right? So you can kind of tell based on the difference between the numbered terms how many times you're multiplying r by itself. So I'm going to write this out as 3r cubed equals 3 over 64. Can I solve for r? Yeah. First, get the 3 times r cubed over to the other side. So I multiply by 1/3. So I get r cubed equals 1 over 64. You might have been able to see that without multiplying by 1/3. And then to find r, take the cube root. Now, these should be small enough and should be familiar enough. So think about on Wednesday, I had you in your warm-up do the list of perfect squares and the list of perfect cubes, that you would be able to do these without the calculator. If you needed your calculator, you call up cube roots, and other roots in the math menu. But what is the cube root of 64? 4. If it's 1/64, it would be 1/4. You do the cube root of 1 over the cube root of 64. So now we have r. We need to find our first term. Oh, why would you just divide 3 by 1/4 to get your first term, Bailey?
Because that's r.
Yeah. R is 1/4.
And a sub
A sub 2, or the second term is 3. So this one's pretty easy. You just have to backtrack once, right? And you're at the first term. So you took the first term times 1/4, and you got 3. So if you have 3, instead of times by 1/4, divide by 1/4. So A sub 1 is 3 divided by 1/4, which is 12. So that worked out really well. I like that idea. Okay. If you wanted to, you could do like we did in the warm-up, like choose one of those as like an ordered pair, n, comma, a sub n, and plug it into the rule and solve. So there are multiple ways to do it, but now I can write the rule. A sub n equals my first term 12 times 1/4 raised to the n minus 1. And could I find the seventh term? Plug in 7 for n. On these problems, geometric, a lot of times you're going to get some decimals. I would just say use your fraction button in your calculator and give exact answers. So I get a sub 7 is 3 over 1024. So most important is that you do some practice with this on the homework assignment. So like you figure out, how would I find the first term? Would I do the same thing that Bailey did, or would I maybe do it more algebraically with an equation? And find out what works for you by doing your problems. Any questions so far? Okay, moving on. I'm going to delete this because I don't like the way that the book has it. Formula for a finite geometric series. So now we're talking about, okay, here are all the terms of the geometric sequence. Let's add them together, right? Because the series is a sum of terms. Okay. Here's how I like to write my series formula. S sub n, where n is however many terms I want to add, just like yesterday, equals a sub 1, my first term, times 1 minus r to the n, and I put that in a group of parentheses, that's my numerator, divided by quantity 1 minus r. So if you look this formula up in the textbook, it's going to have one big set of parentheses around that fraction. I like to put parentheses around the numerator and parentheses around the denominator because that's how you call on your calculator to do the numerator first, then the denominator, and then divide. Okay, so parentheses are going to be really important here. And in my example, I'll just ask that everybody pull out their calculator and try plugging it in so we can make sure everybody's comfortable with all the parentheses here. So first example, we've got summation notation. It's written out for us. We want to find the sum for that summation notation. So I'm going to plug into my formula for a finite geometric sequence, or series, we should say series. How many terms am I adding? 12. So to decide how many terms you're adding, if you're given summation notation, you're going to look at your upper bound. Okay, so S sub 12 equals, I'm going to do my first term, which if you're given summation notation, you can pull it from the rule. The first term is 16, and then I'm going to do my quantities. 1 minus my ratio, which is negative 1/2. If my ratio is negative or a fraction, I am going to protect it with parentheses because this needs to be raised to an exponent, and so I need all of that to be raised to the exponent n. That includes the negative and the fraction 1/2. So I'm going to raise that to the 12th, close my parentheses for the numerator, and then divide by 1 minus negative 1/2. Now, you could type in negative 0.5. You know, I know some people like to do that just because it's less than negative 1 divided by 2. Whatever works for you. Okay, so you could type in negative 0.5 here since 1/2 is terminating. Will you type that into your calculator? And then I want to make sure you can get the same answer as me. So I'm going to put my answer up. And you'll call me over if you are not getting this sum. If you get a decimal, use your fraction button so it matches mine. And I'll walk around and see if you can get it.
Yeah, so I just type it all into the calculator. Okay. And that's why I have those separate parentheses. I mean, I really don't need to rework out the calculator. Okay. We're in pre-calc, so as long as we can type the moving in from calculator, I feel good about that.
Remember, this should be 1 minus r, not 1 minus n. Did you get it? Call me over if yours is not matching. Well, you could try it again. Do you want me to look at what you typed in? Are you sure? You just have to click that button and I'll just start Can I look? And it didn't work out? Oh, it did. You just have to turn it into a fraction. Do you know how to do a fraction? Yeah, do seconds here. It might give you a mixed number, and that's okay. Anybody else having trouble? Anywhere? You guys get it? Not working?
That's the exact same thing again.
Did you print? Nope, parentheses. We have the old parentheses right there. Okay, well, on the negative, minus is not. Oh, okay, now, there are a lot of very nice looking people sitting next to you, and I would hate for you to name them with a packet of paper. Okay, my next example, I just want to clarify directions here. I think there were some problems on the homework assignment for arithmetic that asked you to do the same. When it says use summation notation to write the sum, this is really the goal of the problem, to write summation notation. So I actually don't want to know what the sum is. I just want to see that you could write it in summation notation. That's the thing with sigma. So in terms of sigma, you want to, or summation notation, you want to have the lower bound, the upper bound, and then the rule that comes behind it. So if I were given this series right here, finite, because it doesn't have plus dot dot dot, I want to do summation notation. I'll always assume that the beginning of that series is my first term. And this is my second term, -3. We're talking right at the same time. this is my third term, 3/5, how will I figure out what negative 3 over 625 is, which term it is? Does anybody have any ideas? For us. How about this? Talk real quick with your groups. How do you think you might be able to find out if that's the third, fourth, fifth, sixth, seventh, 10th term? Okay, anybody got any ideas? I heard some good chatter.
Peyton has a good idea.
Peyton, what's your idea?
I don't know. Just like look at the bottom and then be like 5 times 5 equals 25, and then once you correct them, 5 equals 25.
Okay, so you're looking at, yeah, you're looking at the fraction, so you're just ignoring everything else, huh? So he's saying, well, I see that I started to go into fractions, and so I'm going to keep multiplying by 1/5, essentially, is what you're doing. So you're saying the next one is 25, then there's 125, and then there's 625. So this was the third term, this is the fourth, this is the fifth, so this must be the sixth term. Okay, I believe it. Anybody else have other ideas? Some people were just a little bit more particular. Instead of just like looking at the denominator and figuring out the 5, they actually found the ratio. How many groups said find the ratio? Almost all of them said find the ratio. What is the ratio for this one? Negative 1/5. Okay, so I might think about r is equal to negative 1/5. And then you could basically do what Peyton is doing. Pick up at 3/5 and do 3/5 times negative 1/5. Well, that's going to give me negative 3 over 25. Now, that's the fourth term, not the term I want. Multiply by negative 1/5 again. That's going to give me a positive 3 over 125. Okay? Not what I want. Multiply by negative 1/5 again. That's going to get me my negative 3 over 625. So now I know that it's the sixth term again. So I like those.
What if there's like, it goes all the way to like the 30th?
Yeah, so if it goes all the way to the 30th term, then we would do like the rule thing. So we know the first term is 15. We know the ratio is negative 1/5. And it's going to be raised to the n minus 1. And we want to know what 3 over 625 is. Okay. There's a lot of different ways if you do that. You know, you could divide by 15. And then if you want to keep solving algebraically, to solve for a variable at an exponent, you use a logarithm. Or you could then kind of use a guess and check for what the exponent would be. But yeah, you can kind of think about it and try the homework and see what works for you. And then by doing what I just did with Leah, I have my rule, don't I? So I just got to copy that rule right over here. First term times the ratio. So while Peyton didn't find the ratio, at some point he's going to need it for summation notation. And then since I used I down here, I should have I minus 1. These letters should always match. So if you prefer ends only, you just always make them end. That's fine. It doesn't bother me. So what I didn't do there is actually find the sum. I only wrote the summation notation. And that to me is what that direction is asking for. Write the summation notation to represent the sum. Okay, next up is infinite series. Do you recall doing infinite series at all in Algebra 2, anybody? You think maybe no? Okay. Formula for infinite geometric series looks like S. Notice there is no sub n because if you're doing it to infinity, you don't have a number for the number of terms you want to add. Okay, so S equals the first term divided by 1 minus R. If you're doing this in your calculator, that 1 minus R is in the denominator, should be in a group of parentheses. Okay, and there are only some geometric series that have infinite sums. That is when the absolute value of R is less than 1 or greater than 0. So R could be positive or negative, but the absolute value of R should be less than 1. So I could show this to you as an example. I'm standing over here, my desk is over there, and you guys would give me the direction, walk halfway to your desk. So I will walk halfway to my desk, and then you'll say, walk halfway to the desk again. I will walk halfway to your desk. Walk halfway to your desk. Theoretically, do I ever get to the desk? No, but at some point you guys are like, Ms. Cronky, you're not moving anymore, you're at your desk, right? Okay, so when I was standing over here, we could have taken a tape measure and measured the distance to my desk, right? And I would just be adding up those numbers as the distances that I walked. And eventually when I get closer and closer, the numbers I add are so small that you don't even notice them. So I'm approaching some number. Okay? But that only happens if the ratio is a fraction. If I'm doubling the distance that I walk, I just keep walking further and further, and it approaches positive or negative infinity. Okay? So an example real quick about an infinite geometric series. Notice I can tell this series is infinite because it has plus ... and it doesn't end. So I just need to make sure my ratio is less than 1. What is the ratio for this sequence? 1/5. The first term is 5. And that's all I need. S equals 5 divided by 1 minus 1/5. That's 5 divided by 4/5. And dividing by a fraction is multiplying by its reciprocal. So when I add up all these terms, they're going to be approaching 25 over 4, or 6.25. If your ratio turns out to be a number, or its absolute value is greater than 1, then you could just say no sum. I think the book might call it undefined, okay, and that's fine. It's just going to keep getting larger and larger, positive or negative infinity. Okay. Okay, my last example. You're almost there. This is so cool. We're going to find the rational number representation of a repeating decimal without the fraction button in our calculator. Cool. So, when it says find the rational number, what are we going to be, what's our final answer going to look like? A fraction, Gracie says, her favorite kind of number. And right now it looks like a decimal. And it is a repeating decimal, right? So this is important that we have some kind of pattern going on and it does not terminate. Okay. Do you agree that this is really like 0.590990, stuff like that? Okay. So if you want to do this without a calculator, you have to break up that decimal. So notice there's one part of that decimal that's kind of different than the rest. 0.5. Agree? Okay. So we're going to break this up and we're going to have 0.5 out front. And we're going to be adding to that 0.5. And then we're going to break up this stuff behind it into other decimals. So if I wanted to get, like if I rounded it to 0.59, I would do 0.5 plus 0.09. So that this 9 is in the hundredth spot. There'd be a 0 and a 9, and if I add those up, I get 0.59. Okay. The next one would be just 0, right? So that's kind of boring. So I'm going to skip that third piece. I'm not going to write plus 0.000. Boring. So I'm going to go to the next 9. I'd have to have a 0 for the 10th term, a 0 for the 100th term, a 0 in a 1000th term, and then a 9 in the 10,000. So I'd be adding plus 0.0009, because that 9 is in the 4th spot after the decimal. Are we okay with that? And the next 9 is in the 6th spot, so I'd have 5 zeros. Now, when I'm doing my own work, I probably don't write another one. I just get 2 of them. And that just keeps continuing, right? Add 2 more zeros to the next one. Okay, so we're going to focus right now. Remember, this 0.5 was kind of like the oddball. It didn't repeat. Okay, so we're going to focus right now on these because this has a pattern. It's a sequence. And it's geometric. And it keeps going. So it's an infinite geometric sequence. What's the first term of that infinite geometric sequence? 0.09. What's the ratio? One over 100. You could think about it like the second term divided by the first term, 0.0009 divided by 0.09, and that would be 0.01, which is 1 over 100. Okay. Or you could think about this. This is like the way the book will show it. This is 9 over 10 squared because it's in the 100th spot. And then this one is 9 over 10 to the 4th, because it's in the 10,000 spot, so we're multiplying by a 10 squared, or a 1 over 100. I actually like, at this point, to change them into fractions, so I'm going to do that with our 0.01. I'm going to make it 1 over 100. And what would 0.09 be as a fraction? 9 over 100. So now I'm ready to do my sum for all of those numbers. The infinite sum for that series would be 9 over 100 divided by 1 minus 1 over 100. Well, you know, like your whole goal is to get to a fraction, right? So at some point, yes, you should. And then this would be 9 over 100 divided by 99 over 100. 1 minus 1 100th is 99 100ths. It looks kind of ugly there, but it's going to clean up real nice because you multiply by the reciprocal, 9 over 100 times 100 over 99. And then your 100 cancels, and 9 over 99 is 1 over 11. If you're not changing it into a decimal or into a fraction, you're getting like, you're having to use your calculator. But the whole idea here is we could find out the fraction representation without a calculator. All right, so that's not the whole thing, right? That's just the repeating part. 909090. So don't forget about this guy at the very beginning. That's 1/2 plus the sum of everything else, which is 1 over 11. What's a good common denominator? 22. 11 over 22 plus 2 over 22 is 13 over 22. Yay! So if you type 13 over 22 into your calculator and hit enter, it's going to give you 0.590909090. No, am I aware that there is that fraction button in your calculator? Yes, I am very aware of that, but I want you to see this as like, how does the calculator do those things? It understands sequences in series. There's a program written for it, right? We just want to see where that comes from. So you're looking at that and you're using the sequence in series to go back to the rational expression.
Are we gonna have to know how to do it?
No, not on Tuesday. I don't think so. I think you need your calculator. Okay, so you've got about 8 minutes left. You have a homework assignment. I'm going to give you a green sheet, which is, it's called additional review, and it is optional for, like, do you need extra practice with some of the sequence and series? Then you can get extra practice. And I'll probably post the answer key later today, so anyone over the weekend who wants to check their answers can. And then you have a quiz next Tuesday, November 21st, right before Thanksgiving break. That is going to be a graded quiz. So it's not like I'm going to highlight it and give it back to you. I'm going to grade. So you need to be ready. That's why the additional review may be helpful. On Monday, we'll be working with our group to do some fun word problems related to sequences and series. You're welcome. This additional review is really good for just like the basics of like, do I know my rules? Can I work around how to plug into the rules? Okay.